Welcome back to the Dr. Statsalot channel's series on probability theory. I'm Mark Ledbetter, and this is video A of B for part 2 of functions of one random variable. In this lesson, we begin with a review of the goals for section 1. Present the method of inverse substitution for transformations of one discrete random variable and give a short proof. Provide examples of transformations with this technique. Visually depict the transformation. Finally, we will review the key points of the video. Here we have the goals for this section, which we've discussed in the previous 2 videos. So let's get started with this lesson. If we have or can derive a formula for the discrete random variable of interest, say capital X, we can use the inverse substitution method to apply a function or transformation to that random variable. Let's say that we wish to find the distribution for the function u applied to the discrete random variable x. This function u has to have an inverse in order for this method to work. That means that u has to be a one-to-one and onto function. This is also called a bijective function. So we will let y stand for the new random variable for u of x. Once we write out the relationship of y as a function of x, we take the inverse u on both sides of the equal sign. So then we're left with capital X equals u inverse of capital Y. Now we're going to substitute inverse u of lowercase y for the lowercase x in f of capital X equals lowercase x. Then we can have the PMF for the random variable y. And this means that the quantity f of capital Y equals to lowercase y is the same as f of capital X equal to inverse u of lowercase y. So we replace every instance of little x in the PMF of x with the quantity u inverse of lowercase y. Now we provide an easy proof. Our goal is to find an expression for the PMF of random variable y, or equivalently, f of capital Y equals lowercase y. For this proof, we take an inventory of what we know. First, we know the formula for the PMF of random variable capital X. Second, we have a formula for the transformation from x to capital Y. Now we're ready to prove the result. We start with what we wish to obtain, which is f of capital Y equals some specific value of little y. And we use the relation random variable y equals u of random variable x. So we substitute u of x in place of the random variable capital Y. Now we want to solve for the random variable x in the equation. To do this, we need to somehow remove or cancel out the function u on the left-hand side. So we apply the inverse function of u. Remember that whatever we do to one side of the inequality, we have to do to the other side. So now we are left with f of capital X equals u inverse of little y. And for a discrete distribution, this is the same as the probability that capital X equals u inverse of little y. This is the end of our proof because we have shown that the PMF of capital Y at the value little y is equal to f of random variable x at the inverse of u of little y. In the first example, we solved the transformation using the method provided earlier. Now, some statisticians, including myself, prefer to use the method that was used in the proof to solve problems. We will show examples of both so you can choose which method you prefer. So we have a random variable capital X that has a binomial distribution with n equals 3, and the probability p of the event of interest occurring is 1/4. We want to find the distribution of random variable y, which is the exponentiation of random variable x. So our goal is to find p of capital Y equals lowercase y. The PMF of x is the PMF of a binomial random variable with n equals 3 and p equals 1/4. The values the random variable can take are between 0 and n. In this case, that is 0, 1, 2, and 3. Now, recall that the inverse of exponentiation is the log function, and our goal is to solve for capital X in the transformation formula y equals e to the x. the log of lowercase y equals the log of e to the lowercase x, which is just x. We use our procedure and write the probability of capital X equal to some value little x. We replace little x with the log of little y in the PMF for the random variable x, and this gives us the probability of capital X equals to the log of little y. So we've replaced every little x in the PMF of random variable x with the log of lowercase y. Now we have the formula for the PMF of the transformed variable, and we're finished. Next, we wish to find the range of the random variable y. Now that we have the formula of the distribution of y, we need to find the range or space of the random variable y. The PMF is not complete without the range of y, because we have to know what values we are allowed to use in this new distribution. Using a table is an easy way to keep from making a careless mistake. We list out the values of x in the first row. In the second row, we start with the formula for y. So the value of e to the 0 exponent is equal to 1. So we then calculate the remaining values of y. And now we have the complete PMF for y. So what if we want to find the probability that y is equal to 1? We replace little y with the value 1 everywhere in the formula. We end up with 27/64. Now we want to visualize the effect of the transformation on x. It is very important to understand what the transformation is doing to the PMF of random variable x. So in this slide, the distribution of x is in the top Excel graph and the distribution of y is in the bottom Excel graph. The horizontal scales are the same and the vertical scales are the same. Notice how the transformation stretches the distribution of x but not equally. X equals 0 is moved 1 unit to the right. X equals 1 moves about 1 3/4 units to the right, while x equals 3 is shifted over 17 values to the right. Another way to see the effect of the transformation is to connect the dots. This is not generally recommended for discrete distributions because it may incorrectly lead someone to think the distribution is continuous when it is not. Dashed lines have been used to indicate that there are no probabilities between the points. So now we see the effect of this transformation. This first example used the method that is usually taught. However, many of us prefer to use the derivation method from the proof, since it is sometimes easier to remember and may prevent careless errors. Our next example will use the proof's derivation method. In this example, we use the derivation method that we saw in the proof for a simple transformation of a Poisson distribution with lambda equals 2. For this method, we start with the desired outcome, P of capital Y equals lowercase y. We replace capital Y with 2 times capital X. Now our goal is to isolate capital X. To do this, we apply the inverse function to both sides of the equation. The inverse function for 2 is the multiplicative inverse of 2, which is 1 over 2 or 1/2. This, of course, is the same as dividing both sides by 2. However, it is important to realize that this is the inverse function, and this is the method we'll use for more complex functions. We obtain P of capital X equals 1/2 lowercase y. Recall the PMF for a Poisson random variable, and make sure you remember to write out the space of random variable x. We will replace every lowercase x in the PMF with 1/2 y, or y over 2, and we will multiply each value in the space of x by 2. Now we have the result for the PMF of random variable y. We simplify the expression if it makes the PMF simpler. In this case, it does not. So let's say that we wish to find the probability that y equals 2. We plug in 2 for every lowercase y, and the result is approximately 0.271. Next, we visualize this transformation. We show a small portion of the distribution of x on the top Excel graph and the distribution of y on the bottom Excel graph. Remember that the space of x is infinite, so we cannot plot the entire distribution. Here we have plotted the first 6 values. Also, for a 1-to-1 transformation, notice that the values on the vertical scale are exactly the same on both graphs. The only change is their position on the horizontal axes. This transformation stretches the original distribution. Using dotted lines to help us see the shapes reveals that both graphs have the same shape but a different scale. We applied a linear transformation to the space of the distribution. The A is called the scale parameter. Values larger than 1 stretch the width of the distribution. Values less than 1 compress or shrink the width of the distribution. B is a shift parameter. Positive values will shift to the right and negative values shift to the left. We applied y equals 2x, so we only had the scale parameter, and 2 is larger than 1, so the distribution was stretched horizontally. It is always important to understand what effect the transformation has on the distribution whenever possible. In this video, we technically covered everything you need to complete the worksheet. The link is in the notes. However, the next video will cover additional examples which should make the worksheet completion easier. To summarize what we have learned, if we have a formula for a discrete distribution, then we solve the transformation for lowercase x. The PMF of random variable y is equal to the PMF of random variable x, but where we replace lowercase x with the inverse function of u of y. Remember to transform the values of x to y as well, but here you apply the function u, not the inverse function of u. We can use the alternate derivation method from the proof. We start out with what we want, p of capital Y equals lowercase y. We replace capital Y with the function or transformation of capital X and solve for capital X. Then we substitute inverse u of lowercase y for every lowercase x in the PMF of random variable x. Remember to transform the values of x to y as well. One way to see the effect of the transformation is to graph the before and after. Alternately, you could think through the transformation using your knowledge from algebra to sketch the new distribution. Well, that's the end of this video. I certainly hope you have enjoyed it. I also hope you'll take time to complete the worksheet that's provided for this video and the next. When you're completing the worksheet, please take that time to add whatever notes you need to your information sheet so you'll be able to do this in the future without having to search through your notes. Please stay safe and take care of yourself because we hope to see you here next time.